Hello and welcome to video 7 in Module 7. In this video, we'll conduct a two-tailed hypothesis test. So let's get started. According to colleges.com, the mean age of students attending a community college is 29 years old. Gary suspects that this might not be true of students at Mohawk Valley Community College. He finds a simple random sample of 50 students and determines that they have a mean age of 23 years old. Assuming that the population standard deviation is 6 years, conduct a two-tailed test at the O1 level to determine whether or not students at MVCC have the same mean age as other community college students. And we're going to round interim values to the nearest thousandth if needed. Okay, so there's a lot of information here, so we're going to conduct a hypothesis test. So we want to break down that information into a useful summary. First, before I bother to do any of that though, I need to make sure, can we in fact do a hypothesis test? To determine whether you can do a hypothesis test, you need either a sample size that is more than 30 or a population that is approximately normal. In this case, Gary found a simple random sample of 50 students, so we have our SRS and we have a sample size more than 50. So yes, we can do more than 30, sorry. So yes, we can do a hypothesis test. Next, if we're going to do a hypothesis test, we have to state our hypotheses, right? So in this case, we want to know what information is Gary contesting and what does he suspect. For the part that he's contesting, Gary thinks that there's a difference between students at MV and just students at community colleges in general. So we're told that the mean age of students attending a community college is 29 years old. Okay? This is the thought that Gary is contesting. So our null hypothesis is going to be that mu equals 29 years old. Gary's suspicion is that the students at MV are different. So we're going to conduct a two-tailed test. A two-tailed test is where we have a not equals to. So we're going to have mu is not equal to 29 years old. And the last bit of hypothesis information to collect is the alpha level. And in this case, it says to conduct the two-tailed test at the alpha equals 0.1 level. So alpha is going to be 0.1. Next, we're going to collect all the other information and just kind of list it out so it's easy for us to have to reference. So the usual suspects, the usual information to collect are going to be the population mean, the population standard deviation, the sample size, and our sample mean. Now, the population mean you can either pull from the paragraph. It will also be the same as our null hypothesis. So whatever number you use in the null hypothesis should be the same as the number you use in your alternate hypothesis is going to be the same as the number you use for mu. So this is why we have 29 years old appearing 3 times already. It's the same in the null and the alternate, and that's what we're going to use as mu. So sometimes I have a hard time stating my null and alternate hypotheses. I'm not sure what number or what mean to use. So I sometimes find it useful to do the collect the usual information first and then use that to help me form my hypotheses. Then reading through the paragraph, we have sigma is 6 years, so that's our sigma value. For n, Gary found a simple random sample of 50 students, so n is going to be 50 students. And when he looked at his sample, he determined that his sample had a mean age of 23 years old. So x bar is going to be 23 years old. Now, I also want to point out a couple of cautions here, or a couple of things that tend to be confusing. One of the confusing parts of a hypothesis test is that you will always have 2 different means. You'll have a population mean and you'll have a sample mean. And it's going to be important that we recognize which one is for the population and which one is for the sample. In this case, the mean age of students attending community colleges in general was 29 years old, so that is going to be the population mean. That's for mu. Gary's sample had a mean of 23 years old, so that was our X bar. That was for our sample mean. Another thing that can be a challenge, especially if you collect the usual information before you find your hypothesis test, is that you cannot let the X bar inform your alternate hypothesis. So, for example, a common mistake on a problem like this one is to say that since X bar was 23, that's smaller than mu. So a common mistake is to have an H1 that says mu is less than 23. You can't do that because in practice, what happens in reality, you form your hypotheses first and then you get your sample mean. So you don't have a sample mean available to you when you form your null and your alternate hypotheses. The reason we do here in this math class is because, you're not going to go out and do this experiment. I'm going to give you all this information to help you kind of work through the steps of how to conduct this test. So even though you have the sample mean available to you, you can't use that for your alternate hypothesis. So to form the alternate hypothesis, always look at the suspicion. What does the person think is going to happen? Or in this case, we were told specifically to conduct a two-tailed test. So we're going to use that to form our alternate hypothesis. Okay, so now that we've summarized the information, I'm going to wipe away this paragraph of text so we have a little bit more space to work. And now we're going to find the usual information. So we're going to find a sigma x bar, a z, and the p-value. This is the mathy part of a hypothesis test. Now our formula for sigma x bar is the same as it always has been. It's going to be sigma over the square root of n. Since I have this nice summary on the right-hand side, I know that this is going to be 6 over the square root of 50. And we were told to round interim values to the nearest thousandth. So this is about 0.849. So my sigma x bar is going to be 0.849 years. For the z-score, we're going to use a formula based off of the central limit theorem. So our z-score is going to be x bar minus mu all over the standard error. Now, with the central limit theorem formula for z-score, we had x bar minus mu x bar over sigma x bar. But remember that mu x bar is the same as mu. So I've just written mu in this formula just to make our lives easier for the hypothesis test. If we can make it a little bit easier, then we'll do our best here. So I plug in my values. This is going to be 23, since that was the x bar, minus 29, because that was mu, and we're going to divide that by the standard error of 0.849. And we were told to round to the nearest thousandth, so if I went to the nearest thousandth here, this would be fine. I chose to go to the nearest hundredth because it's a z-score. So I put my z-score as a negative 7.07. Now, this is a really large z-score. Normally our z-scores are like negative 3 point something or 3 point something at, a maximum. Now, but this is okay for this problem. This is what we get. And since we're doing a two-tailed test for our z-score, we need to make sure we have two z-scores. So I'm going to list this as plus minus 7.07. You'll only do this for a two-tailed test. If I was conducting a left tail or right tail, if I had mu was less than 29 or mu was more than 29, then I would just put that negative 7.07. I would just put whatever I got. But for a two-tailed test, we need both the positive and the negative. Lastly, we're going to find our p-value. So to find the p-value, I'm going to draw a picture of my standard normal curve, and I'm going to shade appropriately. For shading, I'm going to shade below the negative z-score and above the positive z-score. So when I draw my picture, here's what it's going to look like. So the reason that this type of test is called a two-tailed test is because when I look at the graph, there are two little tails that have been shaded in, one to the left of negative 7.07 and one to the right of positive 7.07. Now, because the standard normal curve is symmetric, this means that that shaded area on the left-hand side is going to be the same as the shaded area on the right-hand side. So for a two-tailed test, basically what we're going to do is find the area on the left below the negative z-score, and then we'll double it because the area above the positive z-score is the same. When we use our table to look up the negative z-score, it's not on there. It's literally off the charts. So there is a point where it says if you're below negative, I think it's like 3.69 or something like that. If you're below a certain cutoff, then we're just going to use 0.0001. So this area to the left of the negative 7.07 is 0.0001. The area above positive 7.07 is the same, so I'm going to double it, multiply it by 2, and I end up getting 0.0002. So this means our p-value is 0.0002. So that's how you find a p-value for a two-tailed test. Now that we've done all the math parts, we can conduct our analysis. So here's our analysis and the conclusion. To determine whether we should reject or fail to reject the null hypothesis, we have to compare a p-value to our alpha, our significance level. This means we have to compare 0.0002 to the alpha level of 0.01. Now, 0.0002 is like 0.02%. It's super small, which is definitely smaller than 0.01 or 1%. So our p-value is less than alpha. This means that if the mean age of students at MVCC was 29 years old, Gary would have gotten the sample that he got less than 1% of the time. Okay, so in fact, he would only get it about 0.02% of the time. So this is extremely weird. Gary's sample is a weird sample. It is statistically significant. So we will reject the null hypothesis since the results are statistically significant at, we use the 0.01 level. So when you reject the null hypothesis, that means the alternate hypothesis wins. So the alternate hypothesis is going to be our conclusion. So our alternate was that mu was not 29 years old. In this case, mu is standing in for the MVCC average, mean age. So we are able to conclude that students at MVCC have a different mean age than other community college students. Since our alternate was that mu was different from this 29, this is how we're able to draw our conclusion. Please make sure that when you're drawing a conclusion for a hypothesis test, you do relate back to the context of the problem. So it's not enough to say we're able to conclude mu is not 29 years old. I need to know, well, the mean of what? What were you comparing your values to? So in this case, we were comparing students at MV with other community college students in general. That concludes our video of a two-tailed test. In the next video, we'll do an example of a left-tailed test. Thanks for watching, and have a great day.